So these statements, we're going to also want to look at those statements on the board, because if acceleration is 0, that means the object is not accelerating, or there is no acceleration, and our velocity is constant. If it has any acceleration, whether it's a positive or negative, that's not 0. That means it is accelerating, which means our velocities are going to change. So what I want you to do is go through your 9 graphs, your 9 velocity versus time graphs. I would write, there should be 4 letters written by each graph, and then I want you to go through and kind of draw some general conclusions. That if we have an object whose velocity is 0, then I'm looking for a line that is, and now I'm looking for above the 0 line. And it might look like in a couple quick sketches. Okay, it's the same ideas that we did in the position versus time graph conclusions. Now we're just looking at velocity. Remember, velocity versus time graphs, we've got to switch gears. The slope of a velocity versus time graph gives us acceleration, not velocity. That's a position versus time graph. Velocities versus time graph, the slope give us acceleration. So I'm going to give you some time to go through, kind of work through this sheet, draw your conclusions. I will go through these conclusions with you to kind of make sure we're all on the same page, and I'll talk about a few things. I do have a quiz that I'm going to, a progress quiz, just to kind of see where we're at, like we did before. That we'll go through, we'll deal with velocity versus time graphs. So if you have questions on velocity versus time graphs, make sure you get those answered ahead of time. Because what I'm going to do is I'm going to give you the quiz and say, hey, here's your quiz, take it. And your answers, just like last time, are going to be posted, and it's going to be for you to check and you to check, and not me look at, unless you say, hey, I don't get this question, which please do if that's the case. Then at the very end of class, I'll start talking about tomorrow's lab, because last hour we had some extra time, bless you, we had some extra time, so I kind of introduced the lab that we're going to do tomorrow. So tomorrow I don't have to spend as much time kind of explaining what's going on. So that's kind of what we're going to do. When you have questions, please let me know, but I'll go through this in a little bit. Is the filled in version that I'm going to show you is posted in Canvas under today's agenda. So that is what I'm going to be showing you. I don't want you just to open it up and copy everything that I already wrote. I want you to try to draw these conclusions with a partner. I'm fine with that, but I want you to try to come up with these conclusions without just copying. Now, if you want to look at it for reference, please do, but let me know what I can do to answer questions. These are also posted in today's agenda, just so if you need to take a better view than on my screen, they're also posted under today's agenda. But a couple trends I want to look at is all of my graphs that were above the line, no matter what shape or slope they have, if they're above the line, that's a positive velocity. Remember, the slope of these graphs give us acceleration. These slopes give us acceleration. So I don't care about these slopes when we talk about velocities. Okay, the slopes give me acceleration. I'm not asking about that yet. The velocity is 0 when the line is like on the line, which is that really thin black line on that darker 0 line. Yes, it is, okay? But that's the idea, is the velocity is 0 when it's on that line and on that line. Negative velocity when it's below. Lots of different ways. You could have a straight line, a flat line, a downward sloping line, or an upward sloping line. But as long as it's below the line, it has a negative velocity. As long as it's above the line, it has a positive velocity. If it's on that 0 line, and when I say line, I mean on the 0 line, then there's no velocity. What does a positive velocity tell us? The positive tells us the direction. Positive velocity. Positive direction means that way. Or it could be up to. Okay? So all of these objects are moving in the positive direction to the right. All of these are moving in the negative directions. Okay? The directions are given with the positives and the negatives. When we look for velocity being constant, remember, velocity is constant when there is no acceleration or my acceleration is equal to 0. the slope of a velocity versus time graph is acceleration. So if my slope is 0, then my acceleration is 0, which means it's not accelerating and my velocity is constant. So we're looking for flat lines. This line right here is a constant, it's meant to be straight, it was a little crooked, is a flat line with a positive velocity. Velocity is constant. This is a negative velocity with constant velocity. This is 0 velocity, but the velocity is still constant. It's not changing, it's staying at 0. That's also a 0 velocity, but a constant velocity. If my velocity is changing, it starts at some value that's different than some other value. I think there's really like a fourth one here, but it doesn't matter whether it's a positive slope or a negative slope, it's got a slope. The slope does not equal 0. Because the slope of a velocity versus time graph is acceleration, so if my slope is not 0, my acceleration is not 0, which means it is accelerating, which means my velocity is changing. We're looking for different things on these graphs because we're interpreting these graphs differently. If my velocity is constant, it means my acceleration is 0. These two statements are one and the same. Constant velocity acceleration is equal to 0. These two are identical to one another. D and F. If D is true, then F is always going to be true as well. Now, if my velocity is changing, there's two types of changing velocity. We have where my acceleration is not 0, which means it is accelerating. That's what it means, it is accelerating. And it's positive, so it means it has a positive slope. Because the slope of a velocity versus time graph is acceleration, and if my acceleration is positive, that means my slope must be positive as well. That's a positive slope, and that's a positive slope. This is a positive slope with a positive velocity. This is a negative velocity with a positive slope. But the slope is positive, that's why the acceleration is positive. These are negative accelerations because these are negative slopes. Notice how I'm not saying decelerating. I don't use that term. We talk about positive velocities and negative velocities. Because you can have a negative velocity with a negative acceleration, and you're going to speed up. Because the negatives tell me the direction, the positives tell me direction. So an acceleration that is negative means it's accelerating that way. The acceleration is in the negative direction. That's what a negative acceleration tells us. If my velocity is constant and my acceleration is 0, which for our purposes on these graphs, because we're only looking in the x direction or the y direction, then my object's speed is also going to stay the same. My speed will stay the same if there's constant velocity, no acceleration, acceleration is equal to 0. Because we're only talking about left and right or up and down. Now that's different if I'm walking like this and I change direction. I just accelerated, but my graph that's a two-dimensional problem. Okay, so an object is slowing down versus an object is speeding up. Remember, this right here is 0 meters per second. If we're getting closer to 0, it means we're slowing down. If we're getting closer to 0, that means we're slowing down. We slow down when it approaches the 0 mark. We slow down when it approaches the 0 mark. Okay, so when objects are speeding up, they're getting further away from that 0 line. They're getting further away. Now, the slope is not 0, which means they are accelerating, and then we're getting further or closer. I did write these two things, and we'll talk about those more as we kind of get further along. But when we talk about an object slowing down or speeding up, I use my fingers a lot for directions. So if my velocity is in the positive direction, finger to the right, and my acceleration is also to the right, so I'm moving that way and I'm accelerating that way. What's going to happen to my speed? Moving that way, and now I'm going to accelerate in that direction. Faster or slower? faster, right? Okay, I'm accelerating in the positive direction with my positive velocity. Now what if I'm moving in the negative direction and I accelerate in the negative direction? I might go faster or slower? Faster. I'm just moving in the negative direction. And if you say, wait, how can you, fine, I'm moving that way and I accelerate that way. Oh, I'm moving faster. Okay, now let's put the negatives. I'm moving in the negative direction, I'm accelerating in the negative direction. If my velocity and acceleration are in the same directions, they're speeding up. So positive, positive, negative, negative. However, if they're in opposite directions, that's when we're slowing down. I'm traveling this way, the positive direction, but my car is accelerating this way, stepping on the brakes. Okay? Or the wind is slowing me down. Whatever, we won't go there. Okay? Or if I'm moving in the negative direction, but I'm accelerating in the positive direction, I'm going to slow down. Gravity works that way too. Gravity always pulls down, right? So if I throw a ball up into the air, my velocity is up, but my gravity is pulling down, it's causing acceleration down. What does that ball do as it goes up? It slows down. And eventually it stops, and it starts to come back down. And because gravity is pulling it down, and the ball is moving down, what happens to the speed of that ball because of gravity? It speeds up. Same directions. Okay, they're in the same direction. So that's another way we can think about those. On graphs, maybe not so much, but when we start putting numbers with these, a positive velocity with a positive acceleration, that thing should go faster. Negative and negative, it's going to go faster. It's just going to go faster than the negative direction. So those were meant to be kind of some takeaways from those graphs. And hopefully you kind of got a basic understanding of velocity versus time graphs. And we'll see, I guess, in a second. What I'm setting out on the back table and on the front cart is a progress quiz called Velocity versus Time Graphs. It's very similar to the one that you took the other day that was called Position versus Time Graphs, except for now these are velocity graphs. The first 5 questions are general questions about motion graphs. The rest of them are, you're going to choose one A, B, or a C. You're going to choose one of the two. You're going to one of these 3 and one of these 3. These types of questions are questions I expect you to be able to answer, and I'm going to evaluate next week sometime. We'll take a quiz on motion graphs, and I'll enter it as an S1 content standard because S1 is going to be 1D motion. So this is part of your 1D motion grade. So these quizzes that we're practicing right now are really for you to get feedback to yourself about, hey, do I really understand these or not? Once again, I have the answer keys posted on that lab table and that lab table, and they're listed in today's agenda. So the answers aren't the important thing, once again. And it's easy to trick yourself, especially when you're circling something. Oh, the velocity is positive, and then you go check it. Oh, it's negative. Yep, you're right, it's negative. But if you truly don't understand why it's negative, please ask someone. Even if you don't want to ask me, make sure you ask someone so you can get those questions answered, because next week, I'm going to ask you to do this without any of that feedback from your friends or help from your friends, or, hey, I'm just going to check the answers before I submit this. So let me know what questions I can answer on these. The quiz next week will be almost identical format as the one that you have there or there. It might be electronic, but the format will be the same. A circle which choice is the right choice. So when you have questions, or if you have questions, please get help from someone and let me know what I can do. In the lab, we're going to take a marble and we're going to set these ramps, and we're going to roll a marble down the ramp and we're going to let it roll across the lab table. And what we're going to do is we're going to time the amount of, we're going to use they're called photo gates. And a photo gate is nothing more than it's a light sensor that we can set a beam of light towards, and as long as the beam hits the sensor, we're good. Once something passes through it, it breaks the beam and it can start an electronic timer. So if we use one of them and we know the distance, we can calculate speed, but we're going to use 2, and they become like a stopwatch. So as the marble rolls through the first photo gate, it starts a stopwatch, and it rolls and it rolls and it rolls, and it stops the stopwatch very precisely. Hundredths or even thousandths of a second. And the idea is, if you know exactly how far apart your photo gates are, you know your distance, your delta x, It'll tell you your time. You can calculate the speed between those two gates. Now, important thing is we want to be consistent with our measurements. So if we're going to measure from the far left side of my first photo gate, I need to measure to the far left side of my right photo gate. Same thing if I go to the right side is fine, or if we go middle, we just got to go to the middle. We just got to be consistent. All three of those methods are fine. And then what we're going to do is we're going to roll it. We're going to calculate the velocity, 3 calculations. And we're going to move it. And then we're going to do it again at a different distance. And we're going to do it again at a different distance. And at all of those distances, we can calculate, we know we're going to measure how far apart the photo gates are. And we can time them. And then we can make a position versus time graph. And we can look at a velocity versus time graph. And we can draw some conclusions about the motion of this object's, of the ball's motion. The nice thing is, well, the bad thing is you're going to do like 27 trials of rolling a ball down a ramp, which is pretty quick because you roll a ball and you roll a ball and you roll a ball. That means 27 velocity calculations. However, we can do what's called a calculated column, and it'll do a lot of those calculations for us. And then what we can do is, just like when with the fish tank, we can type an IP address in and it will take it and you will get your data on your iPad. Same thing we can do with this lab data. So we have our graphs, and then we can tell our iPads, what do we want to graph using graphical analysis? Do we want position versus time? Do we want velocity versus time? We can look at the slope of those objects and we can talk about, is the speed increasing, decreasing, velocity constant, is it changing, stuff like that. Okay. The frustrating part for most students is when you roll a marble down the ramp, at some point that marble is going to hit the gate and tip it over. So then you got to make some adjustments, you got to move your photo gates, and you got to remeasure. You got to remeasure a lot, because if a photo gate gets knocked off, you got to readjust so you know the distances between the two. Also, our tables aren't necessarily always flat, so you sometimes get like a curveball that you kind of got to arc through the photo gates. But it's something that's not too bad. So that's tomorrow's lab, basically. And then we'll go through and you'll be able to analyze some of the data, just like your motion graphs that we have been analyzing. Okay? We'll quiz on this stuff next week. So if you have questions, make sure you get those taken care of. Have a good day.